Hi everyone, Mrs. Pesic here.
And Miss Bella here.
And we're looking at section 1.1, Exploring Transformations. While we're doing this section, while you're looking at the notes, while you're looking at the video, please take good notes. The objectives are to apply transformations to points and sets of points and to interpret transformations of real-world data. Your vocabulary: transformation, translation, reflection, stretch, and compression. A transformation is a change in the position, size, or shape of a figure, and you did learn about this in geometry. A translation or slide is a transformation that moves each point in a figure the same distance in the same direction. Again, we studied this in geometry.
So our first example is going to be translating points. So we're going to perform the given translation on the point -3, 4. So remember, just a refresher, when I plot the point -3, 4, that first ordered pair is the x's. So I travel 1, 2, 3 to the left, and then +4 up on the y-axis. We're going to find out what will be the new coordinate of the translated point. So for A here, we're going to move it 5 units to the right. So I look at the point I have right here, and if I move it 5 to the right, that's going to affect the x-axis, or the x value. So 1, 2, 3, 4, 5. My new point would end up right there. So we're going to end up at the point 2, so 2 to the right if I start at the origin, and then up 4. Again, that's kind of the same as just taking our x value and adding on 5 to move it to its new position. For part B, we're going to do two things, so 2 to the left, and then we'll do 2 down. So let's take care of 2 units to the left. Again, starting with our original point here, so let's get rid of this, at -3, 4. To move 2 to the left, we're going to take that x and move it over. So if I was at -3, and if I subtract 2 from that, that's going to now end up at -5. And I'm going to move it 2 down, so my point would be right about here. If I move that 1, 2 units down, I'm going to have 4 and subtract 2 from that. That will end up at +2. So my new ordered pair will be at -5, +2.
All right, so notice when you translate left or right, the x coordinate changes, and when you translate up or down, the y coordinate changes. So horizontal translation, each point shifts left or right by a certain number of units. So if, for example, you're going to shift a point 3 units to the right, a horizontal shift of 3 to the right, you can just add 3 to your original x coordinate, or to every x coordinate. And if you're going to shift something to up or down, the y coordinate changes. So if you want to take 1, 2, for example, and shift it 2 units up, you would add 2 to the y coordinate. So you go to the left if h is less than 0, and you go to the right if h is greater than 0. And you go down if k is less than 0, and up if k is greater than 0.
A reflection is going to be a transformation that flips a figure across a line called the line of reflection. Each reflected point is the same distance from the line of reflection, but on the opposite side of the line. Again, this is something that you would have talked about in geometry when we talked about doing some reflections. So 2 examples here. We have a reflection across the y-axis. So if I think about that, that means I would, if I had a piece of paper here, I'm going to fold this on the y-axis. So my x coordinate is going to change. If my original point in this case was at the point 1, 2, so this is that one here in red, if I reflected it across the y-axis, it was 1 unit away here, so it ends up 1 unit away on the left, which is how I got my new ordered pair at -1, 2. So the pattern, if you're going across the y, is you're changing the x. You're making it negative of what it was, the same distance away, but on the left-hand side. If we reflect across the x-axis, well, now we're thinking of the x-axis as being the line that I fold across. So right here, that's where I would maybe fold this graph in half. If my original point was at 1, 2, that was 2 units away. So when I reflect that down, it will be 2 units below it. So again, using that rule, my y value is going to become negative. So instead of moving that many units up, you will move that many units down.
And if you had a point that was if you had a point down here, for example, let's say, 4, -1, and you want to reflect that across the x-axis, that would appear up here at 4, +1. Again, you just want to take the y and make it the opposite of what it was if you're reflecting across the x-axis. And you want to take your x and make it whatever, take your x and make it the opposite of whatever you wanted if you're reflecting across the y-axis.
All right, so when we talk about transforming a function, we're going to transform each of its ordered pairs. So when a function is translated or reflected, the original graph and the graph of the transformation are congruent. So again, there's a vocab word that you've had from last year. So when we say they're congruent, we mean that they are the same size and shape as each other. So again, by doing a transformation, we're going to keep the same size and shape, just shift it on where it is on our graph. So let's take a look at our example 2 here. We're going to use a table to help us take the graph given and perform some transformations. So for part A, I want to translate 2 units up. So before I do this, it's important to find some points from the graph, and we're going to make a table. We're going to choose 5 points off of this that will help us maintain the shape of this graph. So if we take a look at these, we're going to pick 1, 2, 3, 4, 5. So points that really help us see what this graph looked like. So let's list those 5 on our table. So I'm going to go left to right here. So I'll start off with my x-coordinate was -3, and my y-coordinate was -1. Then I have -2, 0, 0, -2, 2, 0, and 3, -1. So you kind of know what we're starting with. This problem asks us to translate 2 units up. So the first thing I want to think about, is that going to affect my x-coordinate or my y-coordinate? Since I'm moving up and down, that is going to affect my y. So I'm going to use this column right here to help me find out what my new y value will be. Since I'm moving it 2 up, I know I need to add 2 to each of those y coordinates. So I'm going to leave x as is. So my new y here, if I take -1 plus 2, we'll just write out this first one, that is going to become +1. Again, 0 plus 2 will become +2. We'll get a 0, a +2, and a +1. So when I go to graph my translated function here, in this case, I'm going to be using, my x's never change, so I'll still use these, but the ordered pair I'll match them with will come from this column here.
The x's did not change because this was a vertical translation, so we're only moving the y's in this example.
Correct, so we're only going up and down. So I'm going to plot my new points, -3, 1, -2, 2, 0, 0, 2, 2, and 3, 1. And we'll see that this kind of just slid right up on the graph.
What am I doing?
3, 1. You're good so far. One more. 3, 1.
That's not. This one's supposed to be up.
Oh, up one more. All right, well, let's back it up here for a second. There we go. Okay, so we're going to go over to 2, 2. No, that one was right. I think this one over here needed to come down a spot. And 3, 1. So if we draw this in, we see that our new graph will look something like this. You can see that it just came directly up 2 units from the original.
Yeah, and ignore that point that Mrs. Pesic put on there. That was a blunder.
All right, let's try another one of these.
Okay, so this time we're going to take this graph and we're going to reflect it across the x-axis. Again, let's get 5 ordered pairs that we can plot here. So if we take these 1, 2, 3, 4, 5 points, and we can fill those on, -3, -1, -2, 0, 0, -2, 2, 0, and 3, -1. This time we want to reflect it across the x-axis. So does that mean we're going to be changing the x coordinates or the y coordinates to get our new points? Well, if we're reflecting across the x-axis, that means our graph is going to end up mirroring over the x-axis, so it's going to end up like this. That means our y coordinates are going to change, not our x's. So let's change all of our y coordinates to make them the opposite of what they were. So let's make the opposite of -1 is a +1, opposite of 0 is still 0, opposite of -2 is +2, and so on. And now we can plot these points. Again, we are plotting the x column with our new y's. And when we do that, we get -3, 1, -2, 0, 0, 2, 2, 0, and 3, 1. And so that graph, do we have that to show? Does it pop up? Yep. There it is. All right.
Now, imagine grasping 2 points on the graph of a function that lie on opposite sides of the y-axis. If you were to pull those points away from the y-axis, you would create a horizontal stretch of the graph. If you would push those points toward the y-axis, you would create a horizontal compression. So when we do a stretch or a compression, they are not going to be congruent to the original graph because we're changing the size and shape a little bit. So kind of just some visuals to help us here. Um, if we are looking at horizontal, so that's what we just kind of talked about above there, at each point, if I'm stretching, each point is pulled away from the y-axis. So take a look at this original graph. Originally, we had it in blue. If you imagine grabbing this corner and taking it out, we would create what that graph in red looks like, and that would be a horizontal stretch. Compared to directly below this, a compression, if I took the original graph in blue in this case, and I took those two endpoints and I pushed it in, I pushed it toward the y-axis, that would be a compression. So it's not as wide in this case. Similarly, if you look at the vertical over here in this right column, if you look at our original graph again in blue in this case, and I take a point above and below the x-axis and pull them away from that, I'm going to create a vertical stretch, and if I had this one in blue down here and I push those toward the x-axis, I would get a vertical compression. So depending on which way you're changing it, if you're doing a horizontal stretch or compression, your x-coordinate is going to change because that is your horizontal axis. So in a stretch, you'll notice in this one, what happened? Well, I went from the ordered pair 4, 0, and now I multiplied it. I made it larger, so it became 8, 0. So that is a stretch. Compared to a compression, you'll notice I have a factor of a half here that I multiplied by, and I'm going to end up with a smaller x-coordinate for my new point. So if you're multiplying by a number that is absolute value greater than 1, then it's going to be a stretch, compared to if that absolute value falls between 0 and 1, that is going to be a compression. Those same rules apply when you're doing vertical. If you are multiplying the y-coordinate by something with absolute value of greater than 1, it is a stretch, compared to if it is between 0 and 1, that is a compression.
Okay, so let's take a look at example 3. We're practicing stretching and compressing functions. Use a table to perform a horizontal stretch of the function y equals f of x by a factor of 3. So we want to do a horizontal stretch by a factor of 3 with this graph that we see here. We're going to graph the function and the transformation on the same coordinate plane. So let's identify some ordered pairs from our original graph. So I see we have -1, 3, and 0, 0, and it looks like 2, 2, and let's say 5, 2, and I guess that's good. Okay, and so if we want to do a horizontal stretch, do we want to use this column here or this column? Well, which are we going to be changing? Are we going to be changing the x or the y? A horizontal stretch is going to change the x coordinate, and so we're going to be working with this, these x coordinates. We're going to multiply them all by 3. So instead of -1, we're going to have -3. 0 times 3 is still 0. 2 times 3 is 6. 5 times 3 is 15. So what we really want to graph then is this new x column and our y column. So if I plot -3, 3, that's right here, and 0, 0, and 6, 2, and 15, 2 is going to be off my graph, but I think we'll get the idea of what's happening here. This piece goes here, this kind of curves around like this, and then comes straight out like that. And do we have this one up here too? And there it is, looking something like that. Okay.
All right. So let's do a little application with this. So the graph shows the cost of painting based on the number of cans of paint used. So you notice that your x-axis, the independent axis, is number of cans. The y-axis is the cost. So it says, sketch a graph to represent the cost of a can of paint doubling and identify that transformation from the original graph. So we need to look at this part right here. It says the cost of paint is doubling. Well, based on my x and y-axis, it looks like cost here is on my y-axis. So I'm going to need to take each y-coordinate and double it. So looking at our graph right now, when my x was 1, my y was 50. When my x was 2, my y was 100. So I'm actually going to be doubling each of those ordered pairs only the y coordinate to double the cost of paint. So I'm just going to kind of draw it on here. If x stayed 1, instead of having the cost be $50, that's now at 100. When x is 2, instead of costing $100, if I double 100, I'm up at 200. Hopefully we see this pattern. At 3, now I'm up at 300, and I'm kind of going to be off my graph here, and it would look something similar to this. Kind of a zoomed in version of that. You know, if I had some smaller numbers to adjust there, you could see that the blue would be the original and that pinkish red would be what the new cost would be. So what type of transformation would that be? Well, if I doubled my y values, that is going to be a vertical change, and since I'm multiplying by 2, that's going to be a vertical stretch of 2.
Okay, and that's it for this video. Hope you took good notes, and we'll see you next time.